Chapter 3, Scientific Measurement. All right, we're going to break this chapter up into about 10-minute segments. There's a lot of information in it, and frankly, it's all quite important. It's things that you'll build on, and so we don't want to gloss over it and skip over it, but I don't want to give it to you all at once either. So we're going to jump through this and talk about each of these concepts in about 10-minute segments, and I'll have a few questions as you go along to work through. But I will make it so you can skip forward and backwards, since if you know this, I don't think you need to take the time. But if you don't know it yet, this will be a good opportunity to review these concepts that you've read about in the chapter. First of all, there are different types of observations that we make when we look at an object, a substance, a liquid, whatever it is. There's certain types of observations we make. Some of these observations are qualitative and some are quantitative. What's the difference between these two types of observations? A qualitative observation is simply something that describes that object in words. Okay, so you might be saying the object is blue. That would be qualitative. You might be saying that it is hard. That would be qualitative. You might say that it is soft. That would be qualitative. All of these are qualitative observations. Okay, they require words to describe them. You might even just say that it's cold. Okay, that also would be qualitative. Okay, now when we put numbers in those observations, then we have a quantitative observation. So some examples of quantitative observations are the object is 12 inches in length. Another one would be the drink is 3 liters. Okay, or the runner took 60 seconds. Okay, all of these are quantitative measurements simply because they involve numbers. That's really the key difference. Qualitative observations are words, quantitative observations include numbers. Scientific notation. Now this is something that you're going to use throughout chemistry. So you want to learn how to do it, okay? Now, if you come across a number like this one, okay, this has a lot of zeros. It has about 6 zeros. It has exactly 6 zeros. But you'll have numbers that have even many more zeros than that. Okay, and it would be a pain if you had to count all of the zeros every single time. So scientists have come up with a way to describe this number, and they describe it this way. You'll see it down here, 1.32 times by 10 to the 8th. Okay, so this means the exact same thing as this. I'm going to put a double arrow here to show that. Both of these are the same number. Let me show you how this works. If I came across this scientific notation, and if I didn't know what number it referred to, all I would have to do is I would have to look at this 8 here. It is a positive 8. Okay, so here's what I would do. I would go 1.32, and then because there's a positive 8 here, I would move this decimal 8 places to the right. So that's 2, 3, 4, 5, 6, 7, 8. Okay, so I'm moving the decimal to here. Okay, and now we go 0, 0, 0, 0, 0, 0. All right, now you see this number, after I've moved my decimal this many times over, it becomes 132, 0, 0, 0, 0, 0, 0. You can see that that is the exact same number as we had above. So this 8 here kind of becomes some instructions for the student or scientist who sees this number later on. So they know exactly how many times you have to move that decimal to get to your original number. Something important about scientific notation. When you're writing scientific notation, it always has only one digit to the left of the decimal. Okay, all of the other digits are to the right of the decimal. So you have to find a way to move that decimal enough times to where you only have one digit to the left of the decimal. Now let me show you one more example because we just showed how to go from scientific notation to the original number. Let's see how we go from the original number to scientific notation. Let's use a different example. We're going to keep it pretty simple. Let's use 1200 and let's just use 1200. Okay. All right, so now we want to write this in scientific notation. Okay, so our decimal would be right here if we had a decimal. In order to get it so that there's only one digit to the left of the decimal, we'd have to move the decimal once, twice, 3 times. Okay, All right, so our scientific notation is going to be 1.2. And now we have to imagine if we were moving this back to where it was originally, we go times by 10 to the, we had to move it 3 times to the right. That's what we'll have to do, is we'll have to move it 3 times to the right to get back to what we originally had. So we're going to put a 3 up here. All right. Now here's the opposite case. Here we have the zeros before we get to the digits. Okay, we have a very small number. Okay, now to make this in scientific notation, we want to move our decimal over. There's once, twice, 3 times, 4 times, 5 times, 6 times. Okay, so we'd come up with 5.46. Just 1 second. Times by 10 to the, now remember, we moved the decimal over how many times? 1, 2, 3, 4, 5, 6. 6 times we moved it. Now we have to think about it this way. To get back to our original number, we have to move it 6 times to the left this time. Okay, we moved it to the right to come up with the scientific notation, but to get back to our original number, we have to move it to the left. So when it goes to the left, we use a negative number, 10 to the negative 6th. Okay, and that's exactly what we have here. So this is the scientific notation, and it equals the exact same thing as this number. All right, now I know scientific notation can be a little bit confusing. All right, initially when you get into it, it will be a little bit challenging, but again, it is a shortcut. It is going to make your life much easier, but it will take a little bit of persistence to make sure you get it down. So take the time. I've got a couple of sample questions to the right. Finish those, and then come in and ask me those questions if you have some additional questions. All right, 2 concepts we're going to talk about when it comes to measurements. We have accuracy and precision. Okay, accuracy is how close a measurement is to the true value. Okay, so sometimes you will know the true value. For example, you may have a cube of silver that came in a box, and it says on it that this is 5.00 grams of silver, which is Ag, again based on a Latin term that doesn't align with the spelling of silver. All right, when you have an accurate scale, maybe your scale might measure, one measurement might measure 6, one measurement might measure 4 grams, and one measurement might measure 5 grams. Now as you can see, on average, these 3 measurements come out to be 5 grams. Okay, so you would say, okay, that scale is relatively accurate. Okay, when you average those values together, you get very close to your true value up here. Okay, another scale maybe measures 7 grams, 8 grams, and 8 grams. Okay, now the average of these comes out to be, I think, about 7.66 grams. Okay, but we were just going to leave that. Let's leave it at about, we'll leave it 7.66 grams. Okay, so these measurements would not be very accurate. I'm going to put an X through it, not accurate. Okay, they're pretty far off from the true value of 5 grams. Okay, now something about these is that even though they're relatively accurate, they're not very precise. That's our next concept, precise. Precise is how close the measurements are to each other. Okay, now these measurements are all within 1 gram of each other. Okay, but maybe you have another scale that measures like this, 5.01 grams, 5.02 grams, 5.00 grams. Okay, this would be very precise. Okay, each of these measurements are within 1/100th or 2/100ths of each other, within 2/100ths of each other. The scale measures to the 100ths place. Okay, that makes that scale very precise. Okay, now sometimes you're going to have a scale that could be, now this happens to be both precise and accurate. This up here happened to be accurate, but not precise. You're only measuring to the ones place. That's not very precise at all. This was not accurate nor precise. And there will be cases where you're going to get a measurement that is precise but not accurate. Okay, that would be an example. An example of that would be if you had a measurement of 6.01, 6.03, and 6.02. Okay, if those were your measurements and your true value was this 5.00 grams that we already talked about, this would be an example of something that is precise because they're measured to the 100th place. Each of these measurements are very close to each other to the 100th place, but it's not accurate. They're off by nearly a gram. And this can happen when your scale has not been calibrated. Then sometimes your measurements will be completely off. They'll be very precise measurements, but they won't even be very close to each other or close to the accurate, or there'll be very precise measurements, but they won't be very close to the accurate value. Okay, here are three targets just to give you a little bit of a metaphor for these concepts. As you can see, these three arrows are not very close to each other, okay, so they wouldn't be precise, and they're also not very near the bullseye, so they're not accurate either. These three are very close to each other. That means that they're precise. The person shooting this is very precise, okay, but they're not very accurate. They need to shift everything over to get near the bullseye. This one is both accurate and precise. As you can see, these three arrows are right on the bullseye and they're all close together. That would be accurate and precise. All right, the final thing we're going to talk about here is error, okay, and percent error. Okay, when you have an accepted value, that usually will mean that you have a value that's published in a table. This is a value that several labs have confirmed, maybe several college labs, maybe several professional labs, and everybody agrees on the correct measurement. Okay, this, for example, would be like the density of gold, which we talked about earlier. There's an accepted value for the density of gold. Then there is the experimental value down here. The experimental value is the value that you get when you are conducting your experiment. Okay, the experimental value may not be very close to the accepted value. Sometimes it may be far off. Maybe you had a spill. Maybe some of the chemicals were not pure. They could have been contaminated. Okay, maybe something was wrong about the experiment, and there was a variable that we didn't expect. All of these things can affect your experimental value, and they can affect how close that experimental value is to the accepted value. So then we get experimental error. Okay, so all we have to do to get our error is take the experimental value minus the accepted value. Let's stick with our number that we had before, 5.00 grams. And imagine that we were in an experiment and we measured our substance as 4.50 grams. Okay, to figure out the error, we've got error equals, like it says here, your experimental value, 4.50 grams, minus your accepted value, 5.00 grams. And then our error then, of course, would be negative 0.5 grams. Now, this is a little bit messed up here, so I'm going to rewrite it. It's just got, the formatting got a little bit shifted. So we're going to be talking about percent error. All we do is we take the absolute value of the error and divide it by the accepted value. Okay, and then we multiply all of that by 100%. Okay, so let's look at this example up here. Our percent error is going to be the absolute value of negative 0.50 grams divided by the accepted value, which is 5.00 grams. Now, of course, the absolute value of negative 0.50 grams is going to be positive 0.50 grams. Now, of course, we're going to be multiplying this by 100%. Okay, so let's figure this out. We've got 0.50 grams divided by 5.00 grams. Okay, and then we need to multiply this by 100%. Okay, and I've figured this out before, but it's kind of easy to figure out even in your mind. 0.5 divided by 5.00 is about not about exactly, 0.10, and then we have to multiply that by 100%. and so that is going to equal 10%. Okay, so our error would be 10%. If you have a question on that, again, come and ask me. I'll have a question on the side for you to practice. Finally, this last image just shows some of the different balances that you might be using. This is your most accurate balance. As you can see, it measures to the 1,000th place. This one, and I said accurate, but what I should have said was precise. I actually mix those up a lot. I know the difference, but when I'm talking about it, for some reason I use accurate rather than precise. This is the most precise scale. This would be your second most precise scale. This is called a triple beam balance. Okay, it is quite precise as well, but maybe it measures usually I think to the 100th place. So we'll put 0.01, the 100th place. Now this would be the least precise. This is kind of like a scale you use to measure your food if you're counting your calories or something like that. And in this case, maybe it's only good to the 10th place, like 0.1. So this would be the least, I'll get it right this time, precise. All right, hopefully that helped you understand some of those initial concepts of Chapter 3, and I'll continue on the next video as we jump into a fun topic that is one that will come up all of the time, and it's good to get down now, is significant figures. Look forward to talking to you then.